Hello. Recently I've been experimenting with smaller, more simple patches. When I completed the most recent one, I thought it would also be a good candidate for a patch from scratch. So in this tutorial, I'm going to go over the way this patch was constructed. The starting idea was to use the Resonator module to play notes and have it vary in intensity over time, both in the amount of notes it plays and the way it sounds. The resulting patch will sound something like this. To start off, we need something that generates a note sequence. The Caudal module by Vult can provide this for us. This module generates multiple moving voltages based on an internal model of a segmented pendulum, resulting in several semi-random outputs. Let's add in an oscilloscope to visualize this. Connect it to the first output. Slow down the oscilloscope a bit. And now you can see the output moving up and down. But it is moving between plus and minus 5 volts, which is too much for us since it would cover 10 octaves. I want to have 2 octaves for this patch, so we need to reduce that range. We could scale it down using an attenuverter, for example with the 8-Vert module by VCV. Connect one of the inputs to the Caudal output, send the resulting output to the oscilloscope, and now we can control the scale of the output using this knob, increasing the scale as we open it up. If we set this to 20%, then the output will be scaled down by a fifth. So between 1 and minus 1 volt, but that will also reduce the velocity of the movement. Translated into a 1 volt per octave signal, the original signal contains more note changes, while the scaled down version will give less notes in our sequence. I want to keep the velocity of the original signal, and instead of scaling it down, I want to limit it to that 2 octave range. This is something that the Solim module can do. On this module you specify a lower and upper limits, and it will take the input signal and add or remove 1 volt from it until it falls within those limits. So on the scope you can see that it moves as fast as the original signal, but within a 1 volt range. Let's change that limit to 0.5 volts for the lower and 2.5 for the upper limit. And now any voltage above that will get octaves removed until it is lower again, and anything below that will have octaves added, which results in a voltage signal with the same amount of movement, but limited to the 2 octave range instead. Right now the signal is moving a bit too fast, which is good to see what is going on, but let's change the Caudal speed to minus 0.4, which gives us a more gradual movement that we can now quantize to actual notes. Add in the Quantizer by VCV. Click and drag to disable all notes, and I'll use a C minor pentatonic scale. So that's a C, an E flat, an F, a G, and a B flat. Send the Solim output through the Quantizer, and now we have a quantized sequence that we can use as note source for our patch. We can remove the oscilloscope now, and we also don't need this cable anymore. And to play the notes, we'll add in the Resonator module by Audible Instruments. This module models resonating audio. You could, for example, think of the way that strings on a guitar resonate when you hit them. You can provide an audio input signal to this module, but if you don't, it will generate one internally and use that instead. You then provide it with a 1 volt per octave pitch input, for which we'll use the note sequence that we created. Each time a trigger is sent to the strum input, it will simulate a hit on the resonator, but if you don't connect this input, the module will instead detect changes on the pitch input and trigger a strum each time it detects a change, which is what we'll do here. So let's hook that up to our output. But it is playing only 1 note at a time on the left side. That is because the polyphony is currently green, so set to 1. If we click it once to change it, it turns yellow. Now it will play 2 notes overlapping, alternating between the left and right side. Let's also change the way it sounds a bit, because there are different resonator types. If we click this button once, it will turn to the second resonator type, which in the right click menu we can see is the sympathetic strings resonator, which is the one I want to use for this patch. To broaden the sound a bit, we'll also add in some reverb using the Plateau by Valley. Set the amount of reverb to 25%, send the left output to the reverb, and the right output. Increase the modulation depth a bit to 6%, and close down the input filter, and the reverb filter a bit. So So now the resonator is playing a random note sequence. Right now this all sounds a bit chaotic, because a new note is triggered anytime this voltage changes, which is based on a semi-random source. To bring a bit more structure into this, we'll have to take control over the timing of the changes, which we can do with a simple sample and hold module by Bogaudio. We provide an input signal to this module, and each time it receives a trigger on its gate, it will sample the input signal and use that on its output. So we need a clock for this gate input. Since we don't need a complex clock here, we can just use an LFO for this, like the LLFO from Bogaudio. Switch it to a square wave, and now the LFO output can be used as a clock with the rate of the LFO frequency. For dispatch that will be 4 Hz, so 4 beats per second. Connect that to the sample and hold, use the note sequence as input signal, and send the output to the resonator. Now each time a trigger is received, the current note value will be sampled and sent on the output to the resonator, resulting in some more timing in the rhythm. But I don't just want a constant rhythm, I want some more variation in there. So let's add in a module to modify that trigger. I'll use a Music-Ting Modular Turing Machine for this. This module needs a clock input, so that will be our LFO output, and each time it receives a clock trigger, it will modify an internal sequence. The length of that sequence is determined by this knob. We'll set that to 8 steps. And now you can see that sequence on these LEDs. Each time it receives a trigger, it shifts that sequence 1 step to the right, and it will generate a new value for that first value. So each trigger shifts and modifies the sequence. And how it generates this new value is determined by this big knob. On the current middle position, each new value is completely random, but when you start to move the knob to the right, the chance increases that instead of picking a new random value, it will instead take whatever value was removed from the sequence and reuse that at the beginning of the sequence. So when the knob is all the way at its maximum, there is no randomness anymore, but the sequence will instead constantly loop. I'm going to set this a little over halfway between random and constant by giving it a value of 0.67, so it becomes a slowly evolving sequence. And now you can use the sequence in many different ways, depending on which of the outputs of the module you use. I'm going to use one of these outputs over here, which output triggers based on the values in the sequence. The first one matches the first LED, the second matches the second LED, the third one the third, and so on. I'm going to use this first trigger for our sample and hold. Disconnect the LFO and hook it up with the Turing machine instead. So now you don't have that constant LFO trigger anymore, but instead an evolving trigger pattern that is generated by the Turing machine. Now that we have taken a bit more control over the rhythm, let's change the sound a bit, because there are all these knobs to play with the resonator sound. The harmonics in the output signal control how bright the output becomes. Give that a value of 0.4. Dampening controls how long the note sounds, as if you're dampening a string with your hand. Make that semi-short at 0.25. Position simulates strumming the resonator at different positions, just like a guitar string sounds different when plugged in different positions. Let's set that to 0.7. Destruction knob controls the frequency ratios of the different simulated strings. You can hear that vary as you turn the knob. I found that I like a value of 0.45 for dispatch, which altogether results in something that I thought sounds quite pleasing and relaxing. Now we're gonna add an additional effect into the chain. A delay, provided by the delay module of SurgeXT. Send the resonator output into the delay, and then on to the reverb. The first thing I want to change is the mix. I want some more of the original signal in there together with the delay signal, so set that to 75%. And then I also want some modulation on the delay signal. Give it a modulation depth of 7.5% and reduce the rate down to 2 Hz. Something that I like to do with this delay module is to give it some cross feedback, which will cause a left delay to also feed into the right into the left. Set that to 42.5%. And since that adds additional delay signal, I'm going to set the overall feedback depth a bit lower to 35%. The last thing is the delay time itself. Since the left and right delays are both at 1 second, and our main clock is a division of that, the delay starts to overlap with itself. Changing the left delay to 3/4 of a second will cause an offbeat instead, which we can increase further by changing the right delay to 1.75 seconds to give it a longer delay time. And now these different delay times, combined with the cross feedback, will result in more interesting delay rhythms, which also leave more room for the delay modulation to develop. Now that the sound of the patch is going in the right direction, let's turn to the varying intensity that I wanted it to contain. Starting with the rhythm. I want the amount of triggers that are sent to vary over time. To start, I'll add a Bernoulli gate module. This module expects a trigger on its input, and based on the current probability, it will send a trigger either to the A or the B output. Turn the knob to the left, and it goes more towards A, to the right, and it goes more towards B. So let's send our LFO clock into the Bernoulli gate, and the B output to the Turing machine. And now on average 50% of the input triggers will go to either the A or the B output. Let's increase that to 70%, so more of them go to the Turing machine input. And now I want that to change over time, as if you move the knob back and forth, which you can do with the probability inputs. Send a CV signal into that, and it is as if you're turning the knob. And we have additional outputs on the Caudal module, which we know move from -5 to 5 volts. But that amount of voltage would change the probability too much. So instead of using it directly, I'm first going to send it to the 8 Vult module. Set that to 25%, so that the output will move between plus and minus 1.25 volts, which will cause a probability to move slightly back and forth, and thus send slightly more or less triggers to the B output and the Turing machine, varying the amount of movement. But I want to have an additional variation in the triggers. Every now and then I want there to be a quicker burst of triggers on the clock input, as if the LFO frequency was increased. And we have this volt per octave input on the LFO. Sending 1 volt to this input would cause the LFO speed to double to 8 Hz. So I need something to provide a 1 volt signal every now and again, which I can do by using the bottom part of the Bernoulli gate. Instead of letting that send the input trigger to either the A or the B outputs, if I click here to change it into latch mode, then it will always have either the A or the B output set to 10 volts. And each time it receives a trigger, the probability defines how likely it is that it switches which one is set to 10 volts. And it will use the trigger input of the top section if nothing is connected to the bottom input. So I could use this B output as input for the LFO volt per octave. I do need to send it through 8 Vult first, however, to scale it down to 10%, to turn the 10 volts into 1 volt that we can use on the LFO. And now each time output B is high, the LFO rate will double. But it switches too fast now. Turn it down to 25%, and it will switch less often. And since this doubles the LFO frequency, more clock signals are generated, so it will also turn off again more quickly. Now I want it to be even less frequent, so I'm going to turn the probability even further down to 3%. So now we have a varying amount of triggers over time, with the occasional burst in there, resulting in a more dynamic rhythm. Let's go back to the note sequence now. Because Caudal generates a signal that makes smooth movements, the resulting notes also move in the same way. And I think it sounds nice if every now and again a note jumps out of that sequence. For this I'm going to use a Fate module by Geodesics. This module has two inputs that it can process and send to the corresponding outputs. So let's send our generated sequence into one of the inputs and the output back into the quantizer. So it now moves through Fate, but nothing has changed yet. We first have to tell Fate when it has to do something. We need to provide it a trigger to activate it. Let's use the same trigger that we use for the sample and hold. So now Fate can do something each time a new note is captured. Next, we have to tell Fate how often it has to do something, which is done with a free will. At 0, nothing will ever happen. And at 1, Fate will activate for every trigger. So if I set this to 0.1, then on average 1 in every 10 incoming triggers will cause Fate to actually do something. Finally, we need to tell Fate what to do by setting the choices depth. If we turn that to the right, you can see that these lines move up and down, which means that Fate will add or remove a random value from both the left and right inputs. The amount depends on how far you turn the knob. If you turn it to the left, however, the lines connected to the left side point up, and the ones to the right point down. So it will add random voltages to the left side and remove them from the right side. And I wanted to add voltages to my inputs, so I'm going to set it to -0.3. And now every time a trigger is received, there's a 10% chance that it will add a random voltage to the input signal, which will then be quantized and sent into the resonator. You won't always hear it when this happens, but every now and again the change made by Fate will be big enough that you hear a high note jump out of the sequence, which will then also repeat left and right a couple of times in the delay because of the cross feedback. The final variation I wanted to introduce into this patch is on the sound of the resonator. We have our bass sound set up on the main knobs, but there are also these CV inputs to modulate them. And we have more outputs on Caudal that we can use for this. But these are constantly changing voltages, so if we would hook them up directly with the CV inputs, then they would cause the sound to change while the note is playing, which is not what I'm looking for. So let's use the sample and hold again to sync that with the note changes. Add in a MergeSplit4 by Grande. Connect 3 of the Caudal outputs to it. Send the merged polyphonic output into the sample and hold, and if nothing is connected to the gate inputs, it will instead reuse the gate of the top section to also trigger the bottom section. And we can send that back into the split. But it only contains one value, while it received 3. That is because by default, sample and hold uses the trigger input to determine polyphony. That can be changed in the right-click menu. Set polyphony channels to in input instead of gate input, and now the polyphonic input will result in a polyphonic output instead of that monophonic trigger. And we can now use the split outputs on the resonator. Connect the first one to the brightness input and open up the attenuverter to specify how much it should actually modify the brightness. We'll set that to 0.4 here. Use a second CV for the dampening input. And I want it to move around a bit less, so the notes don't become too short or long. So set that to 0.2. And we'll use the final CV for the position input, which we'll set to 0.4 again, so that it can move around a bit more. So now the sound of the resonator will change over time. Now to come back to that strum input of the resonator. We didn't connect anything to it, so a change in the note input will cause a resonator to trigger a strum. But if you were to connect something to that input, like the trigger coming from the Bernoulli gates, then you end up with a more percussive sound, because now you get a hit on the resonator even if the note didn't change. It's all a matter of taste, but my original intention for this patch was for it to move between more present and more relaxed, so I prefer it without the strum connected. And with that, the small patch is completed. I hope it provided you with some useful information and gave you some ideas that you can play with. As always, thank you for watching and happy patching.